All right, everyone. Welcome to kind of a hybrid lecture. So today's meant to be lecture 19, although we didn't quite finish everything that was in lecture 18. So I want to just go back and just have another page of notes on lecture 18, which as a reminder, so we'll share my screen here. So lecture 19 is going to be on star maps. Lecture 18 was on space cameras. So I'm going to scroll all the way up. The unit that we're in now is star trackers. And we talked about how a star tracker is a camera that takes pictures of stars, and you use that pictures of stars to estimate your attitude or your orientation with respect to inertial space. That's the idea. So this whole idea can be broken up into four smaller kind of sub steps, if you will. And I'd like to have one lecture dedicated to each of those, although the space camera lecture has kind of bled over into the star map lecture. So the space camera is saying, we're understanding the physics behind how a camera works, and we're understanding the equations and a mathematical model of a pinhole projection model or a pinhole camera model, which has some distortion, and we use the Brown-Conradi distortion model. And ultimately, we go from physics to pixels in an image. That's the idea. We go from stars in space to pixels in an image. But then the reason that we do all this modeling is so that we can go the other way, right? Because the goal of lecture 18 is to be able to go from pixels in an image to directions to stars in your local frame. That's the idea. So if you know the directions to the stars in your local frame, and you know the directions to the stars in some global frame, now you have an attitude estimation problem, which is what we're going to discuss in lecture 21, Waba's problem. But that's the setup. You need the star vectors in the local frame, the star vectors in the global frame. So in lecture 19, which we're going to talk about today, is the star vectors in the global frame. So those of you that have taken an introductory astronomy course, or anybody who knows the words right ascension and declination, already has a leg up on this. But we're going to talk about the way that, first of all, there are such things as star maps. And second, we're going to talk about how they work. And ultimately, the purpose of a star map is to give us the direction to a star in the direction of the star in some global frame, right? And so then the idea is that once we have the star directions in the global frame and the local frame, it's just an attitude estimation problem. The hardest step, actually, from a theoretical standpoint, is this kind of middle child here, which is an index search. So let's say you've got 3 stars in your image, and you have 3 stars in the star map. How do you know that you're right? How do you know that those stars are those stars? How do you solve the star correlation or the star correspondence problem? And that's actually very tricky. And there's a lot of research and theory that's gone into that. And it turns out that the implementation is relatively straightforward, although you're going to end up having to do some data structures things after lecture 20. So that's going to be a little bit harder in terms of the implementation. And then for Waba's problem, the math is actually relatively rough when we're going through the derivation. And then when the time comes to actually solve it, it's 3 lines in MATLAB. It's very straightforward. So that should not take you too long. I'm expecting that the content from lecture 19 and 20 is going to be the hardest, but I could be wrong. I've been wrong before. So that's our review of kind of the whole unit. And today we're talking about space camera. So the goal is to go from stars in space to pixels in an image, or pixels in an image to stars in space. We talked about how a camera works. We talked about a mathematical model where we treat the star as following pinhole projection. We talked about the camera calibration matrix or the camera intrinsic matrix. We talked about sources of image noise. We talked about optical aberration. We talked about barrel and pincushion, which are 2 types of radial distortion. We talked about tangential distortion. And we talked about how to use the Brown-Conradi mathematical model to undistort your image points, which is great. So that leaves a question which a few people came to me with in the interim since then and said, okay, great, but I don't see how this all fits together. And that's on me. I would have liked to have gotten to that by the end of lecture 18. So we are going to see how it all fits together. And we're also going to talk about one other concept, which is how do you actually find the stars in the image? Like, if you know where the stars are, we can use this math to undistort them. But which pixels are stars in a star field image? Like, it looks like a black rectangle. If you zoom in, you can find some bright pixels, but like, are those pixel stars, and how does that work exactly? So that's kind of the motivating idea behind what we're going to discuss today. So our topic, which is the new material, is star line of sight, LOS is line of sight, estimation in a digital image. Okay, so we're going to start by considering a theoretical perfect camera. So what would have to happen for a camera to be perfect from an optics standpoint, right? Perfect camera would have absolutely no distortion, have absolutely no aberration, and it would have no noise. It would also be perfectly calibrated, meaning the equations which describe the relationship of the pinhole camera model, the relationship between stars in space and pixels on an image, are perfectly understood with no error. So it's perfectly calibrated. And this is a big one, it has a continuous focal plane array, as in there are no pixels. Right? That means that you can distinguish something that is infinitesimally small, right? Because if you don't do that, if you don't assume a continuous focal plane array, what will happen is small things in real life are pixelated in an image, or worse, they all fall onto a single pixel and they just become a square in an image, right? You're stuck playing Minecraft at that point. So what we're saying is, no, this is a continuous focal plane array. So an infinitesimally small thing in the distance, if you have this image and you just keep zooming in, it is resolved on the camera, right? That is a perfect camera. Of course, nothing like this exists, but even in this thought experiment, this camera would still not see a star as a dot. That's kind of my point that I want to get across, and that's because of physics. So this camera would not see a star as a point of light. Okay, why is that? Instead, those of you that remember your discussion of optics in physics might remember, it will detect something called an Airy pattern, which is essentially a diffraction pattern, right? So even a perfect camera still has to deal with the fact that light diffracts when it goes through the pupil, the entrance. That's the idea. So instead, it would detect the Airy pattern, A-I-R-Y, somebody's last name, caused by diffraction at the camera aperture. And I'm not going to try to draw it because I'm going to do a terrible job. It's not that important, but it's essentially a bullseye. You're going to get a bullseye shape. It's going to be this radially symmetric, kind of circular symmetric diffraction pattern. So you're going to get a bullseye for each star in the image with one very large peak in the middle and then trailing off this diffraction pattern. So this actually does happen on some cameras. Some space cameras are so good that if you zoom in enough, you do actually see airy patterns on individual stars. That has been known to happen. So if a detector is sufficiently sensitive to resolve, we're going to talk about what that means in a second, an airy pattern, the problem of finding the centroid of that star is called diffraction limited centroiding, because the main limiting factor, the main bottleneck, is physics itself. Limited centroiding. And so in this case, you could think of something like a telescope. There are telescopes that are sufficiently precise that they can resolve. Resolve would mean that the airy pattern is actually detectable and it's not just a pixelated mess, right? Generally, you can say that you've resolved the airy pattern if it's about 10 or more pixels in diameter on the camera. So you can actually see like, oh yeah, there's a little bullseye in there, as opposed to a blob or a single point of light. So in that case, we fall under diffraction limited centroiding. I say this for your awareness, but this is not what happens in this class. Navigation cameras do not have this problem, typically. Because they are much cheaper and worse. That's the idea. This is diffraction limited centroiding is like the definition of a first world problem. It's like, oh no, my camera is so good that physics itself is plaguing me and I don't know how to centroid my star. We have much worse cameras with other problems. So we're going to talk about that in a second. Navigation cameras do not typically have this problem. They are much worse. Because your navigation camera is not the Hubble Space Telescope. It's probably small enough that you can hold it in your hand. It probably costs a single digit number. I'm trying to think. It's typically less than $100,000 for a navigation camera. Maybe a little bit, maybe possibly more, but typically less than $100,000, as opposed to the millions and millions of dollars that goes into a space telescope, or billions, depending on how you do the bookkeeping. So these are cheap by optic standards, right? Navigation cameras don't have this problem. Instead, what will happen is a star, what's called a point spread function, or PSF, will appear pixelated. And this is what's called detector limited centroiding. And this is where we're going to live. So here's the thing. We actually don't want a camera to be perfectly focused. Okay, why is that? That seems bizarre, right? Here's the problem. I'm going to draw a before and after picture here. So this is your star field image, and let's say that it's zoomed in. Okay. And if your camera is perfectly focused, then what's going to happen is you will have one pixel with all of the light. So this is like a negative, right? Imagine you've got one black pixel in a sea of white. Really, it would be one white pixel in a sea of black, right? Okay, so let's say I picked one of you, and I'll take anybody who's feeling brave and wants to answer a question, because this is not a rhetorical question. Where is the star in this image?
Somewhere within that pixel?
Ah, okay, now let me ask it again. Where within that pixel?
No idea.
Exactly, that's the problem. It could be in the dead center of the pixel, it could be right on the edge, but it's perfectly focused, so all of the light fell into this one bucket. What we as navigators are then forced to do is assume that it's the center, because that's probably a reasonable guess, and just accept some error. But we can actually do better than that. So stick around, Corey. That was Corey, right?
Yes, it was.
Imagine that I intentionally blurred the camera so that what we get instead, this is meant to be like a 3x3 grid here, is one really, really bright pixel. And then this one's a little bit bright, and then it starts to taper off, and not very much going on over here. Now what we've got is kind of this blur, this blob of pixels. And I've drawn it as a 9x9, but really it would be some other weird shape. How would we find the center of that, Corey? What do you think?
Um, do like a sort of weighted average to find out.
Did you read the notes? Did you see
No.
that? No, that's it. That's what you do. So what we call it a center of mass algorithm, but it's basically a weighted average of the pixels. And so phenomenal. Good work on that one, Corey. Somebody had their Wheaties this morning. So we, in practice, intentionally defocus star cameras to aid in centroiding. So the idea is we find a blob of bright pixels. And then the question is, well, what exactly do you mean by bright? And we're going to address that. And then take a weighted average to find the centroid. And in practice, if you use a star tracker that uses this method of, there's actually much, much fancier ways besides weighted average, but weighted average just works so dang well. It's very reliable. The weighted average can generally get you, pardon me, 1/10 of a pixel of centroiding error, which is pretty good. It's a lot better than just guessing the center of the pixel. Let's see. Okay, I have a few notes that I didn't see on my next page that I just said, but I want to make this a little bit more explicit. If all the light from a star falls onto a single pixel, we are forced to take the center of the pixel as the centroid. However, if we intentionally blur the image, we have a point spread function to work with. So scroll down a little bit. There are some fancy centroiding techniques. I spent some time looking into these. So one is to fit a Gaussian, basically a two-dimensional bell curve. So Gaussian fit. Another is to use machine learning or neural nets. So this could be a possible term project for those of you that are still thinking about what you want to do. Alternative methods of centroiding and how to improve on the center of mass method. But in practice, we often default to the weighted average / center of mass technique. And the reason why is because it's fast. And if you're building a star tracker, you will often want it to work at 1 hertz or better. So taking the image, processing the image, finding the centroids, getting the pixel values of those centroids, doing everything that we talk about in the next 4 lectures needs to all run on a flight computer, which is about as powerful as a potato, in 1 second. And so everything you can possibly do to make it as simple as possible is what you will do. Even if it hurts your performance a tiny bit, it's often better to get the data at a 1 second hertz than it is 1 hertz than it is to, okay, well, if we're willing to chew on this for 10 minutes and do some fancy other, Gaussian fit neural nets, we could see a 1% improvement in performance. That's like, it just needs to work. It doesn't need to be perfect, right? That's what we often end up doing in practice. So your centroid, here's the actual equation for that. Your centroid coordinate is the sum of over all I pixels in some blob of the U coordinate and then the intensity at that pixel divided by the sum of all the intensities within the blob. That's the idea. So you take each pixel's u coordinate, multiply it by its intensity, add those together, and then divide that by the sum of the intensities. And similarly, VC is the sum over all I pixels in a blob of VI II over the sum over all pixels in the blob II. That's the idea. This can generally achieve 0.1 pixel centroid error, which is pretty cool. All right, questions on centroiding. Otherwise, we have another quick aside here. All right, so far so good. So the next thing I want to talk about is what's called thresholding. So how do we know where the stars are in an image? So what we're basically going to do, remember I talked about we're looking at blobs of stars. How do you even achieve that? Like if you're booting up MATLAB and you load in an image and you want to process a star field image, right? How do you even know where to start? And one of the things that we do is we say, look, there is some pixel value where everything dimmer than that pixel is the blackness of space or noise, and everything brighter than that pixel is a star or maybe something else. It could be a planet, it could be a bit of dust that happened to pick up some sunlight, but everything brighter than this threshold is worth considering. Everything dimmer is part of the background noise. And so that's the very first thing we're going to do is consider only pixels brighter than some threshold. And that threshold is a tuning parameter that you can choose. There's actually several of those within a star tracker. This is a number where you're going to need to just pick something and then play around with it and see if you can't maybe get performance to improve by changing what that number is. On homework 4, here's a little hint. I recommend that your threshold is a value of 10 out of 255, where everything dimmer is space or the noise in the image. Everything brighter is worth considering. So I think that's a good place to start. And that's based on some analysis that was done on the Artemis 1 flight images that ultimately determined that 10 was a very robust number. You can play around with that a little bit. I wouldn't deviate a ton. I wouldn't use 20 and I wouldn't use like 1. I think you'd be asking for trouble at that point. But so that's your toehold. That's the very first thing you do when you load up the image is you consider only pixels brighter than 10 or some other number if you choose to do something else. That's thresholding. There's one other quick aside, which is star line of sight bearing error. So how do we know what our bearing error is? Or first of all, what is bearing error? So let me ask it another way. Before I said a 0.1 pixel of centroiding error, which means that we have an uncertainty in where the star is in the image that is 1/10 of a pixel across. That's the idea. So what does that mean? What does 0.1 pixel centroiding error, or in this case, bearing uncertainty? Bearing means direction, right? So this is a direction uncertainty. What does that mean as an absolute angle, for example? Well, simple math would be, okay, we know that it's 1/10 of a pixel is how uncertain we are in the bearing direction. So the width of a pixel is just divide that by 10 and then you're done. So what is the width of a pixel as an angle? Well, there's a term for that. The angle swept out by a single pixel is called the instantaneous field of view, or IFOV. Here we go. So the instantaneous field of view. Now, some of you might be saying, now, wait a minute, Paul, there's no way that all the pixels are the same angle. It's like, okay, fair enough. That actually is a problem. There is a bit of a difference. Why is that? Well, essentially, you could think of it this way, right? Here, and don't draw this because this is just a quick sketch. Here's your kind of your pinhole point, and here's your image plane. And let's say that this is one of your pixels, but then, and this is just some distance, it's one. And then let's consider all the way out here. You can just quick thought experiment. This angle is less than this angle, right? So we're going to be considering pixels at the middle of the field of view. That's the idea. So for those of you that were thinking that, those of you that weren't thinking that, just thanks for tagging along on our quick aside. We're going to be considering the width of pixels that are in the middle of the image. And you'll find that there's not a ton of variation across the field of view. So here's the actual image, which you might want to write down. So, and actually it's going to be similar to what we just saw. So let's say this is your image plane. And this is your focal point. The distance between them is 1, or actually as it's set up, yeah, as it's set up, it's 1. And then you just consider this triangle. So this distance is 1, and this angle is your field of view. That's what a field of view means, right? Well, now imagine we drew a similar triangle that was in pixel land, right? This is in pixel land. So it's a similar triangle. We're just going to take the right side of this. And we said, okay, let's consider that this angle is field of view divided by 2. Let's consider that this side length is the number of pixels divided by 2. So it's the width of the image in pixels divided by 2, right? It's the same as this distance over here, except instead of real life, or instead of being in some units of distance, it's in units of pixels, right? By that same logic, this length is dx. Right, we talked about that. So dx, the camera parameter, that is the focal length in pixels. That's the idea. So this triangle and this triangle are similar triangles. And that is actually how you can compute dx given the field of view. So I give you dx in this problem, but you can compute a rough guess of dx if you just know the field of view and the number of pixels. This will come up on homework 6. So you will need to refer back to this lecture for homework 6. But you could also say, okay, what if instead we just consider a much, much narrower triangle where this distance is the IFOV, this distance, or sorry, this angle is the IFOV, this distance is still dx, and then this distance is 1 pixel, right? That's how you would compute your instantaneous field of view, just with a bit of trigonometry. Thus, the bearing error for a star centroid found by a weighted average is 1/10 of the instantaneous field of view. And now that's an actual angle. We could say, oh, it's this many degrees is how sure we are about where the stars are in the image, this kind of thing. Or instead of degrees, you might choose to use arc minutes, which is a 60th of a degree, or arc seconds, which is a 60th of a 60th of a degree. Or you know, we can pick with radians or microradians, whatever you like, but there's some actual angle, not just pixels, right? That's the idea. Okay, so this is where I was hoping to get to with lecture 18. So we just had a little bit more, wanted to talk about line of sight estimation in the digital image, wanted to talk about thresholding, talk about bearing error. And so I just wanted to quickly summarize. So to summarize, and then maybe we'll take a little break. On homework 4, you will take your image, so load the image, threshold the image. So now we're considering only pixels brighter than some threshold. Find star blobs. Find centroids of those star blobs using that weighted average. Okay. Those centroids now need to be converted to image plane coordinates. Towards, and this is using the inverse of the camera intrinsic matrix. Okay, great. Those image plane coordinates have been distorted though, so now we need to undistort. And then finally, when we have our undistorted image plane coordinates, we normalize. And this gives you star line of sight directions in the camera frame, which is the goal of this lecture. So hopefully this gives you what you need to accomplish that. And I'll give you a little hint. Those of you that are using MATLAB, I like a function called BW_CONCOMP, which stands for black-white connected component. So what this will do is if you give it an image that is all black and white, some white pixels and some black pixels, it will tell you where the blobs are, which is really nice. So you can just go ahead and use that instead of writing your own blob finding algorithm. It's not necessary. Everything else you should be able to code up pretty much completely from scratch. And if you have any questions, we can talk about that in office hours. I'll also field some questions right now, but I think this is a good natural pausing point if we want to take a break. And we will be back at 6:44.
I have a question.
Yeah, what can I do for you?
What does that word say right above k to the -1?
Oh, yeah, that was me getting sloppy. That's an abbreviation of coordinates. I can say
Oh,
that.
okay.
Yeah, image plane coordinates.
And then the word under that where it says start. What is
Yeah,
it?
let me try that again. That's supposed to say undistort.
Oh, okay.
There you go.
Thanks.
Yep, and so that's going up to this concept from the end of last class, where you've got a point on your image plane, which you know has been distorted by physics. You need to undo that using these equations. And it's essentially an iterative solution, and you find your undistorted points.
Oh, okay.
All right, I think that's good. It's a good spot to pick back up again. So I want to continue by starting on lecture 19, which is really only going to be about half of class today, which is talking about stellar cartography. So cartography meaning maps, right? A cartographer is somebody who makes maps. And so just as a reminder, I know we talked about this just a little while ago. Step one is the image processing, but step two is kind of on the astronomer and physics side. It's like, where are the stars? Is there a list somewhere written down of where all the stars are? And the answer to that question is no, because there's more stars than we could ever possibly count. But there is a list of all of the stars that we can count that are nearby, that are bright enough to see. And that's close enough for navigators, right? So where are the stars? Is there some list out there? How do you make a star map? So I'm going to list that as not a rhetorical question. So an actual question. Anybody who wants to jump in, and those of you that maybe have some experience with astronomy, or those of you that know the buzzwords right ascension and declination, there is an established way for saying where stars are in some global sense. Does anybody want to weigh in with that?
Looked at homework 4. I know there's a database of star IDs online.
Okay, so that's, you can look at homework 4 because I do outline some of it there. There's actually a kind of procedure for answering the question of where a star is in space. And essentially, you might think that it pretty much just comes down to two directions, right? So let's say that you've got the Earth, it's got some continents, right? And let's say that you've got a star. Well, imagine that there's just some direction. And then imagine that this star is over this way. There's the actual star direction, right? Do you see how with one azimuth angle and one elevation angle, we can describe how to rotate from some direction out this way to where the star is? That's basically the idea. Now, there's more to it than that. There's actually quite a bit more to it than that. But to a first order, that's kind of all we really need. So this first angle, instead of azimuth, we're going to call right ascension. We're going to use the letter alpha. So right ascension. Does that sound familiar? Right ascension? We've heard that one before. The right ascension of the ascending node all the way back in, I think that was orbital mechanics lecture 4, or it might have been lecture 3. No, it was lecture 4. Yep. Big omega is the right ascension of the ascending node. What does that mean? Well, it's an angle of some vector in space that is not an elevation angle. It's kind of in the XY plane, if you will. And it's with respect to what? Well, what is N1? Do you remember what the X direction is in the inertial frame, in the International Celestial Reference Frame? I think we talked about that up here. Wow, my handwriting has actually improved. Can you believe it? I thought it was going to get worse. The x-axis of the International Celestial Reference Frame is the ascending node of the ecliptic plane on the equatorial plane. It's essentially the intersection of the equator, the plane that stretches out from the Earth's equator, and the ecliptic, which is the plane in which we orbit. And this intersection line is sometimes called the vernal equinox. Other times it's called the first point of Aries. It is essentially, I mean, for our purposes, this is just the ICRF X direction. That's it. So some people who've already decided what the global reference frame is, this is the X direction. So some angle off the X direction is your right ascension. We've already heard that word. And then your elevation, we're going to use the letter delta, and this is your declination. So right ascension and declination are the buzzwords that you might have heard if you have some experience with astronomy. Those are the angles that are used to describe the line of sight to a star. All right, so we're gonna write that all down in more detail in a little bit, but that's basically what happens. So that means that in theory, you could just make a table with the right ascension and declination of every star and be done with it. And then it's like, well, we want that with a very high amount of accuracy. And it turns out that there's other parameters that we might care about each star. So for example, well, actually, rather than me give an example, why don't you shout it out? What else might we care about a star besides its right ascension and declination? Any takers?
Apparent magnitude?
Hmm. How bright it is. Yeah, apparent visual magnitude is the brightness of the star as perceived at Earth, which spacecraft are leaving Earth, but for all practical purposes, they're still pretty close to Earth on a global, like a cosmic scale, right? So apparent visual magnitude, we would absolutely care about the brightness of the star, if for no other reason than because our camera is not infinitely sensitive. It's actually blind to extremely dim stars. And thank goodness for that. Actually, that makes the math problem a little bit easier, looking only at the brighter stars. So maybe we want the bright stars and we want their azimuth and elevation or their right ascension and declination. What else do we maybe want to know about stars?
Maybe their size or class.
Size or class would be interesting. And you could also get, this is not exactly where we're going with this, but you can even get information about their spectra and about their chemical composition. But I'm interested especially in how a star looks in an image, right? What might change the apparent direction to a star? So we just said that right ascension and declination tell us where the star is, but aren't stars moving? But how about how much that star is moving? That's what we call proper motion. We might care about that too. Or how far away is the star? That's called parallax, right? So there's a couple of other things that we might want to know as well. And so right now we're just having this discussion. We're going to write it down basically right now. But so these things that we've just described are what are called astrometric parameters. Astrometric parameters, which are used to reconstruct an apparent line of sight to a star. So among other things, a star catalog contains apparent brightness for each star, typically given as apparent visual magnitude, which is what Max said. And a quick aside, apparent visual magnitude in that scale, dimmer is a higher number and brighter is a lower number. And it's kind of an inverse logarithmic scale, right? That's the idea. So the brightest star in the sky, all right, I'm about to say something and then I might be wrong, so maybe I'm dumb, but I'm pretty sure it's Sirius, the dog star, is the brightest star in the sky, which I think has a magnitude of negative 1.3 or something like that. So it's a negative number, right? The dimmest stars that the human eye can see on a perfectly clear night is about 5 or 6, apparent magnitude 5 or 6. That's as dim as the eye can see, right? Now, if you're in Houston or if you're in Albany, New York, and there's light pollution, then it's actually quite a bit less than that, right? So on most nights from my apartment, I'm lucky to be able to see all of Orion, and Orion is mostly brighter stars, right? That kind of thing. And then the dimmer stars are just washed out by light pollution. But that's just to give you an idea. So roundabout apparent magnitude 5 or 6 is about as dim as the eye can go. If you're, I don't know, in the middle of the Mojave Desert and there's no light pollution to speak of, that's about as dim as you can see. And then a very bright star would be around 0 or even a negative number. So that's the idea. Now, this is a run-on sentence here. Among other things, the star catalog contains apparent brightness for each star, as well as astrometric parameters. Astrometric, measuring stars to reconstruct its apparent line of sight. So some examples of these star catalogs, which now we know that a star catalog is really just a data table of astrometric parameters, which is a little bit less cool than like star map sounds really fancy. It's a little bit more boring in real life, but what we can do with it is very cool. Some examples of star catalogs are, there's one called the Yale 1950, which was made in 1950, or I believe its time epoch is 1950. It might be a little bit later than that. Hipparcos, which is my favorite, is what we're going to be using for homework 4, and Gaia. Hipparcos has fewer brighter stars, and Gaia has more dimmer stars. And so, to give a little bit more context on that, both the Hipparcos and the Gaia catalogs were created by the European Space Agency, which launched basically space telescope missions to go catalog every star. And you might be saying, like I said, every star? No, but a lot of stars. How many is a lot? We have some numbers here for you. The Hipparcos catalog, which we'll be using for homework 4, was published in 1997. I was alive. I don't know how many of you were alive. And it has 118,218 stars, ranging from apparent visual magnitude -1.46. I'm guessing that series, we use the lowercase m for apparent visual magnitude. And the dimmest that it goes to is 12.4, but that doesn't mean that it is complete to 12.4. So you might say, it has a 12.4 star. It does not have all stars brighter than 12.4. So the completeness of a catalog is a whole discussion that we're not going to get into for today. We're going to be using the brightest, I think it's 5,000 is how many roughly stars we're going to be dealing with, which is not nearly as many as 118,218. The Gaia catalog, published in 2018, so this is an ongoing task, has 1,692,919,135 stars from apparent magnitude 3 down to 21. And so this might be intuitive to you, but there are many, many more dim stars than there are bright stars, right? The bright stars are generally closer because of inverse square law and also bigger. Now there are big far away stars, but it being far away tends to kind of cancel it out. Brightness does not necessarily equal distance. Brightness does not necessarily equal size, but there's definitely a strong correlation there. So as we go dimmer, we're looking at further away stars, generally speaking, or we're looking at very weak close stars. And there are many, many more of those than there are close bright stars. But for our navigation purposes, we're going to be looking at the close bright stars. We're going to be using Hipparcos, which has really everything we need for this class. And so the dimmer you go, the more stars there are. We will focus the Hipparcos catalog where m is less than or equal to 5.5. That's what we're going to be working with. So how is it that we use right ascension, declination, parallax, which is the distance to a star, proper motion, which is how much the star is moving, and any other information to actually reconstruct its apparent direction? So that's the next thing we're going to discuss, and that is called the standard model. So both Hipparchos. Wow, all right, just kind of, sometimes I can write, sometimes I can. ARCOS. And Gaia catalogs fit stars to the standard model. There are 6 astrometric parameters. So that's what this backwards E means there are 6 astrometric parameters. And those are alpha, which is right ascension, which we already talked about, ascend, S-I-O-N. Delta, which is declination. These are your azimuth and elevation angles. But then there's also, it's basically alpha dot, which we're going to write as mu sub alpha, which is right ascension proper motion. RA is our abbreviation for right ascension. And then mu delta is your declination proper motion. Basically, it's delta dot. So these are angles, and these are the rates of change of those angles. Okay. Then there's also something called parallax, and the symbol that is typically used is like this weird variation on the Greek letter pi, which looks a little bit like omega with a line over it. We're not going to go into a ton of detail on parallax, so if you feel like using a different letter for it, that's fine, because I can't even find this when I'm coding this up in LaTeX or something like that. But this is your parallax angle. You might be saying, wait a minute, Paul, you said parallax is a distance, but now you're telling us that it's an angle. How does that work out? Well, the idea here is if this is the sun, you know it's the sun because it's got light rays coming off of it. And then this is the Earth. And then this is the Earth 6 months later. And let's say you're looking at some star that's way in the distance. Then you're going to form a triangle. And really what you're saying is, this is of course not to scale, what you're saying is the star looks like it moves by some angle over the course of a year, because you basically have a baseline of, this is 1 astronomical unit, the distance from the Earth to the sun. This is another astronomical unit. So with a baseline of 2 astronomical units, this star is going to appear to move by some amount, which is this capital pi, or some weird variation of pi. That's your parallax angle. And actually, we have a unit of distance. Astronomers have decided, well, look, the number of kilometers that a star is away doesn't really mean anything in any final sense, right? Who cares how many kilometers? It's going to be some huge number. Why don't we use something that's easier for us astronomers? We'll use a parallax arc second. So 1 arc second of parallax, arc second is a 60th of a 60th of a degree. So if a star appears to move by 1/60th of 1/60th of a degree over the span of a year with a 2 astronomical unit baseline, it is 1 parallax arc second away, or 1 parsec away. That's where we get the term parsec. As a unit of distance. Anyway, that's a quick aside. Doesn't really matter for this class. We're going to be looking at parallax as an angle, and we're going to talk about how to get it back into a unit of radians. So we'll get there, but this is fine for now. And then finally, there is what's called radial proper motion, which it is rare to get parallax information on a star. Most stars don't have it. It is extremely rare to get radial proper motion information for a star. So we're really going to focus on these 4. But it's nice to know parallax and proper motion. So, questions on that? Feeling okay so far? All right. So we can define a right-handed coordinate frame for each star. And so what's that frame going to look like? Well, let's put the origin at the solar system barycenter, which is where the International Celestial Reference Frame is, right? So the origin is at the solar system barycenter. We're going to define some p direction, and P is in the increasing right ascension direction. We're going to see what that, I'm about to draw a picture in a second that's going to make more sense. But parallax is in the right ascension direction, or not parallax, the letter P. I'm tired, sorry about that. P is in the right ascension direction. Q is in the direction of increasing declination. But who cares about those? We're after L, and these are not to be confused with the parafocal frame P and Q. Why they're also P and Q? It's like, well, there's only so many letters, but I recognize that can be a bit confusing. What we're really after is L, which is the direction along the line of sight. That's our favorite direction. Okay. So what's that going to look like? This is where I'm going to need to color code some things. Can I do it in, I think I can do this in 4 colors. Okay. This is probably the most important diagram today, so we're going to try to do this right. So this is our International Celestial Reference Frame, with the center is at the sun, which doesn't have light rays this time, but you're going to take my word for it. So this is the International Celestial Reference Frame X, Y, and Z. This here is the equatorial reference frame, or sorry, not the equatorial plane. Sorry about that. So this is the equator. I'm drawing it as an ellipse. That's the equatorial plane. And then there's also the ecliptic plane, which is going to look like this. So this is the equatorial plane. And this lower one is the ecliptic plane. And the intersection of the equatorial plane and the ecliptic plane is the ICRF X direction, right? Now let's say that there's some star up here, and it's time to start using fun colors. So here's the star, right? And the direction to the star looks like this. Okay, so far so good. Well, then let's say that the projection of that star direction onto the XY plane is right there. Okay, so then here's time for a fun color. Let's use blue. This is going to be our right ascension angle. That's right ascension. And then red is going to be our declination angle. So this right ascension and declination allows us to direct a line to this star. Now I'm going to use, maybe we'll use orange for the star line of sight. Or yeah, let's use orange. So now this direction is the L direction, which is pointed straight towards the star. Now there's also going to be some Q direction, which is out this way, which is kind of back off at a 90-degree angle from L. And then there's also going to be, and I'm kind of like running out of space here, a P direction, which cuts right through declination. But you can imagine P, Q, and L are all at right angles to each other. L is pointed straight towards the star. P is pointed off such that if you were to increase your declination or your right ascension, it would be the P direction. And then declination is that if you were to increase that, it would be in the Q direction. So I'm kind of tripping over my words here, but you get the idea. That's so you have L, P, and Q. And we can get these directly from the right ascension and declination angles if we basically follow the same procedure that we did for converting latitude and longitude back to Cartesian coordinates, right? So the L direction, you can just think about this for a second, right? Well, how much is L in the X direction? Well, if we take the cosine of delta, that projects L onto the XY plane. And if we take the cosine of alpha, that projects it onto the X direction. So it's going to be cosine of declination, cosine of right ascension, and that gives us our X direction. To project L onto the Y direction, we would take the cosine of declination to project it onto the XY plane, and then the sine of right ascension projects it onto the Y direction. And then if we want to project it onto the Z direction, that's just the sine of declination. Okay, So what is the P direction? Well, the P direction is defined as being, we're going to take just the K vector, the 0, 0, 1 direction, the up direction, and cross that with L. You can just think about it for a second. Up cross L is P. Or do I have that backwards? Nope, yeah, I have that right. Up cross L is P, and then we're just going to take this vector and normalize it. That's what my brackets there mean. So we're going to normalize it to make sure that it is indeed a unit vector. Finally, Q is the easy one, and that is L crossed P. Okay, so that is the local star reference frame, which is true only for that star. You might be saying, well, Paul, why do we care about that? The answer is we're going to need it in a minute, so just bear with me for now. If we choose to write this all out, here's kind of a more drawn out way. You could think of L as being the cosine of delta, the cosine of alpha, the cosine of delta, the sine of alpha, and the sine of delta. P, if you just go through and do the math, is negative sine alpha cosine alpha 0, which makes sense because P has nothing to do with declination. It's going to be in the XY frame. And then Q is going to be a little bit more complicated. Q is negative sine delta cosine alpha, negative sine delta sine alpha, and cosine of delta. There we are. So there's our local LPQ direction. Okay, so we're not done yet. You might say, well, Paul, isn't L the answer? And it is to first order, but there actually are other things that we care about, right? So there is proper motion, parallax, and a whole host of perturbing effects to deal with. So questions on this to start? Hopefully this diagram makes sense to people. Otherwise, we'll talk about classical line of sight perturbing effects. All right, so there's 3 of these that we're going to talk about. The first of these is called time delay, or you might also hear this called the Roemer delay. Okay, what is that? Well, I'm going to draw a picture. I'm going to try to get like just a little bit of LP and Q in there. Okay, there we go. So let's say that this is the sun. There we go. And let's say that the star is off in this direction. So this is the L direction. And let's say that you've got a spacecraft over here, simple 3 rectangles. So clearly that's the body and those are the solar panels, right? Well, then in this situation, what's going to happen is a star's line of sight direction is defined with respect to the solar system barycenter. But in this diagram, and I'm going to try to clean up that dotted line here. In this diagram, the star is actually going to get, or sorry, the spacecraft is going to see each, photon of starlight before the sun would. All right, so let's say that this is your spacecraft position R. This length here is the projection of R onto the line of sight direction. That's the idea there. So let's write that down. Line of sight is defined at the solar system barycenter. What if your spacecraft is ahead or behind? You can think of it as basically being ahead in time or back in time, right? This is a time delay problem because the apparent line of sight at the sun and the apparent line of sight at a receiver that would see the star sooner or would see the star later is actually a tiny bit different. So as drawn, observer time, so as drawn, spacecraft time is ahead of solar system barycenter time for that star. If the star was in a different direction, that might not be true. And so we can just correct that, right? We're going to say that T solar system barycenter is your observer time plus 1 over the speed of light times this distance, L transpose R, right? That's how much longer. Now that's probably going to be a very small amount of time, but it's not nothing, and it's something that we do want to take into account. So this typically perturbs stars. This effect perturbs stars by less than 1 micro arc second in Earth's orbit. And then just a quick aside. So an arc minute is 1/60th of a degree. An arc second is 1/60th of 1/60th of 1 degree. This is often abbreviated as AS. A micro arc second is, what's that? 1 times 10 to the negative 6th times 1/60th times 1/60th times a degree. Right? Now, this might sound like that's so small that nobody would ever care, but a milli arc second is detectable by not extremely sophisticated optics. So 1 milli arc second is very small, but that's something that we can accomplish. Like we can actually detect those changes with telescopes. I mean, not with your phone camera, but that is something that we would want to take into account. Astronomers are going to care about this effect a lot more than us navigators are. So this Romer delay is going to be optional for you to consider on your homework assignment. If you want to punch that in, you can just consider how much of a time delay is going to be caused by the spacecraft's position, wherever it is. Actually, given that you aren't given the position of the spacecraft on homework 4, I guess you could use the Earth's position. I do believe I give you the rough time when this happened, but I think you'd probably be barking up an unnecessary tree. So we're just going to leave this as an academic construct. We're not really going to be dealing with Romer delay that much on homework 4. Proper motion, we absolutely will consider. Proper motion definitely matters, especially, well, we'll see in a second. Proper motion. The stars have all moved since the catalog was made. So when the time comes to download the Hipparcos catalog, which you will need to do for this homework assignment, it will tell you the right ascension and declination in the J2000 frame at the J2000 epoch, meaning this is what the sky looked like on January 1st, 2000 at noon Greenwich Mean Time. Right? It has been 24 years since then, and some of the stars have moved a not negligible amount since then. Like we really do need to take that into account, right? As a matter of fact, proper motion is actually one of the effects that is a limiting lifetime factor on star catalogs that are used for navigation, because some of the nearby stars that we really like to use are also moving at a pretty fast clip. And so actually, when you're putting together a star catalog for navigation, you might need to consider ignoring some high proper motion stars, simply because let's say you make the catalog for, let's say, August 2022, and then Artemis 1 gets delayed until November of 2022. That's 4 months of those stars moving in the sky, and you can't access the flight computer during that period, right? So these are things you need to think about. Proper motion is probably the #1 effect that we're going to deal with in this class, and you'll definitely need to take this into account on homework 4. Now, of course, some more than others, right? Not all stars have the same proper motion. And I should say that proper motion is not really linked to a star's velocity per se. It's linked to how much it looks like it's moving in the night sky, which is not as interesting if you were an astrophysicist and you want to actually know the state of a star, but for navigators, that suits us just fine. It tells us, okay, here's where the star is and here's how much it looks like it's moving. That's plenty for us. Proper motion is often given in milli-arcseconds per year. So you will need to convert to radians per second. And well, let's start putting this together. So let's say that and this is not the final equation, but this is a kind of intermediate equation, right? Let's say that our line of sight direction to a star is U with a hat on it and I. This is the line of sight direction to the star in the world frame. What is that? Well, it's going to be basically L, because we said that L is the direction to a star as we've set it up. But it will have also moved some due to proper motion. It will have moved some amount in the P direction due to right ascension proper motion, and it will have moved some in the Q direction due to declination proper motion. That's why we bothered to define the P and the Q directions. They're going to come in handy right now. So I'm going to think of it as, well, it's L plus some delta T, which don't write delta T. I'm going to fix this later, times what? Proper motion in the right ascension direction, that's P, plus declination proper motion in the Q direction. And then there's also, if you have access to it, radial proper motion, which is in the L direction. Okay. And then we're going to take all of this. Now, what exactly do I mean by delta T? Well, it's really the solar system barycenter time. So the current time, right? This is if you want to take into account Romer delay, minus what's called the epoch time. And that is when the catalog is defined. And we take all of this and then we normalize it. And that is the line of sight direction to a star. But we're still not done. There's one more thing we're going to take into account. But so just to get this idea here, this is 3 dimensions of proper motion. This is the catalog start time or epoch time. This is the current time. So if we're using the Hipparcos catalog and we're using it for, let's say, November of 2022 for whatever reason, like maybe on homework 4, then it would be 22 years, 11 months, so on and so forth, is going to be this delta T term. And then this is kind of the original catalog line of sight direction. And then this is the actual. But we're going to see an even more complete equation coming along in a second here. Now, should mention that one can neglect radial proper motion if this data is not available. This is not typically a huge perturbing effect. All right, so far so good. Finally, the third one is parallax. And this is not the same parallax, as confusing as it is, not the same parallax that we talked about in the, the fact that we use this 2 astronomical unit baseline to detect the distance to stars, to nearby stars at least. Some stars are so small that they don't even move appreciably. What we're talking about is the fact that your spacecraft is not at the solar system barycenter, and that is an additional source of parallax. So we need to take that into account as well. Also, I should note that I'm looking at the clock and we are actually not that far away from being done. So don't get too upset. We are going to go a little bit later today, but not nearly anywhere near 2 hours. So just hang in there. So as a quick aside, if we were in interstellar space, we were careening from Earth to, let's say, Proxima Centauri, we would need to use a star's full 3D position to estimate line of sight. In the solar system, thankfully, in the solar system, we treat parallax as a perturbation. And so let's say that you've got the sun, and you've got some spacecraft, which is at some position R. And let's say that you've got a star, which is all the way up here. And let's say that this distance is, well, this vector is really rho L, right? Where this is the actual L direction. Okay. What this vector would need to be then is rho prime L prime. So this is the actual apparent direction from the spacecraft to the star, which is what you would really be seeing with your navigation camera. And so in our circumstances, if rho is much, much greater than R, then this triangle starts to kind of close up, and we can say that rho is approximately equal to rho prime, which means, if that's the case, that rho L, this vector on the left, is basically the same as if you take the vector from the sun to the spacecraft and add rho L prime. This is not necessarily true, but it's pretty close. And if that's the case, then we can just do some fun math. L prime is L minus 1 over rho R. So you need to know the distance to the star, but that gives you your perturbation to go from L to L prime. Now, how does this work its way back into our equation for the standard model? Well, we'll see here. This is where 1 over rho is this pi-looking thing, is the parallax term. And if we combine, so this is the, here comes the punchline. Combining Romer delay, proper motion, and parallax gives us the standard model. And this is the big thing that we need. So get ready. UI is equal to the line of sight as predicted by the catalog plus solar system barycenter time minus epoch time times U alpha in the P direction plus U delta in the Q direction plus U radial in the L direction minus parallax times your spacecraft's position converted to astronomical units. And then all of this normalized. Now, I say that, but this term is optional. And this term is also optional. I believe I used parallax on homework 4. You don't necessarily need to if you don't want to. It's not the end of the world. Partially because you don't know the position of the spacecraft. You don't know RFT. You could say that, well, it's traveling between the Earth and the Moon, so it's probably going to be pretty close to the Earth, and we know the Earth's position. If you're an overachiever, that's fine. If you want to, you can go back and use this equation, and that would probably be totally fine for homework 4. So this is the standard model. Now, this is where I would like to talk about, and I have 2.5 pages of notes on relativistic perturbing effects of starlight. So we talked about classical perturbing effects. What about relativity? And we're just not going to get to that today. I've decided to throw that overboard in the interest of finishing everything up. So rather than going into a gory description of those, I'm just going to spend about maybe 2 minutes on each with a quick picture, and that's it. So there are also relativistic, forgot how to spell for a second, perturbing effects. And this is not on homework 4. So the first of these is gravitational deflection. You can think of it this way. Let's say that you've got some spacecraft with a camera. And let's say that you've got some star right here. But let's also say that you've got Jupiter right here. Got a big old spot. That's Jupiter. All right. What's going to happen is the starlight is going to bend around Jupiter, but so the kind of direction that it looks like it is, because you're looking in a straight direction, it kind of looks like it's out here, but that's wrong, right? This is the actual direction. This is the apparent direction. So this gravitational perturbation of starlight is going to impact our line of sight direction. So let's say that the direction from you to this body, which in this case is Jupiter, this is UB, there's going to be some UI prime, where prime means that it's been perturbed, and the angle between them is going to be called theta IB. And there's some equations which we're not going to go into, which you can use to predict what UI prime is. And this gravitational deflection is not negligible. It actually changes how close you can look to certain stars for navigation. If they're close enough to the sun, I mean, yes, you have stray light effects, but you also reach a point where the sun perturbs the stars an appreciable amount, and it becomes a problem. So that is gravitational deflection. There's another one called stellar aberration, which we do take into account. You won't need to for your homework, but stellar aberration, you could think of it as this way. Imagine that you've got, this is going to be a little time-lapse diagram here. Imagine that you've got your telescope, which I'm just going to draw as a light bucket, a bucket for light to fall into. And imagine that you've got a photon coming in from the top of the screen. Here's the photon, right? Then let's say that this is your bucket at time 1, but the bucket is zooming to the right. Right? In that case, at some future time, it looks like this. Here it is at T2. And then at some still future time, T3, the photon will hit the back of the bucket and register as a pixel on your camera. Now, we know darn well that incoming starlight is this way. But you just got a light, a photon on one of your pixels, and your camera was pointed this way. So I'm going to write as UI double prime. So what gives? This is caused by your instrument velocity. And the punchline here is that if you are moving in a certain direction, just the fact that you're, and I guess I'll kind of complete the perspective on this. If you're moving in a certain direction, that will change the apparent direction to incoming starlight. And it's a little bit like how if you're walking in the rain, you hold your umbrella straight up, but if you start running in the rain, even if the rain's falling straight down, you have to kind of cock the umbrella forward so that it catches the drops that would hit your legs and feet, right? That sort of idea. So the apparent direction to incoming raindrops changes when you break into a run. The apparent direction to incoming starlight changes when your spacecraft is moving at a healthy clip. And we do need to take this into account for real spacecraft. This is a perturbing effect, which leaves us at this UI double prime. And actually, more recently, it's been considered that couldn't we work backwards, where if we know where the star is supposed to be and we know where it looks like it is, we can actually measure our stellar aberration. And rather than model it as a perturbation effect, why don't we make that the thing that we're measuring, and we can use that to estimate our velocity. So you can get a direct velocity estimate from stellar aberration. That's called StarNav, and that was developed at RPI, which I think is kind of neat. and that is a currently in development navigation technique, which is being considered for future space missions. So I thought I'd mention that. It's part of our local history. But that is plenty about stars for today, and I want to get you all out of here at a reasonable time. I will mention stellar aberration. There's something called star nav, which is using stellar aberration as your measurement model. And this would be a great term project, and one that I could help you with because I did some work on star nav. So just thought I'd mention that. Now, in summary, on homework 4, you will. So we've talked about a lot of stuff today. How does this help us? Well, let's go back to our diagram in lecture 18, right? So we talked about star maps today. What this means is we need to be able to go download, say, the Hipparcos catalog, which is going to be a database. It's going to be a CSV file, basically, comma-separated variable file, a big old table of astrometric parameters. And we need to be able to write a MATLAB script or a Python script, which loads in that table and then produces a line of sight direction for each star using the standard model. So I would recommend you go download Hipparcos, and you can choose when you're downloading Hipparcos to consider only stars with apparent visual magnitude less than 5.5. And here are the things that you're going to need. You're going to need the Hipparcos identifier. You're going to need its apparent visual magnitude. You're going to need its right ascension in the International Celestial Reference System, its declination in the International Celestial Reference System, its parallax, PLX, its proper motion in the right ascension direction, and its proper motion in the declination direction. So you're going to get a big old table with 1, 2, 3, 4, 5, 6, 7 things in each row, and there's going to be as many rows as there are stars in the catalog brighter than 5.5, which I think is between 4 and 5,000, but I can't remember the exact number. I have a CSV table, so I'm part of the homework assignment is to go to the website and actually download this and learn how to deal with finicky astronomy websites. If you get absolutely stuck, like beyond all recognition, you're completely stumped, I do just have this data table as a CSV file that I could post online, but I thought it'd be more interesting to just go do this for yourself. If you're hopelessly stuck, I could be convinced to post that, but I want you to try it on your own first. Then you need to be able to reconstruct the line of sight to each star using the standard model. And that's it. That's basically all we need to do. So for the material of this class, go download the Hipparcos catalog. That might give you a little bit of a headache, but it shouldn't be too bad. Now's a good time to become comfortable reading in CSV files or using like the read matrix command in MATLAB. Ultimately, you want to put something together which spits out a 3-element unit vector for each star in the Hipparcos catalog. That's the idea. And we're going to use those next time to work on star identification. So the lecture 18 homework is be able to find star directions in the camera frame. The lecture 19 homework is be able to find star directions in the catalog or inertial frame. And then next class, we'll talk about how to correlate those stars, which is the star identification problem. But that is plenty for today. I'm going to wrap up. We went a little bit over time, but I think we covered everything that's essential. Class is dismissed. Thanks for coming, but I'm going to stick around in case you have any questions.